Hi, my name is Zachary Waldaba, and I will be presenting my research project on lift. Our theories of lift has changed dramatically, and the old theories of lift have been used as puzzle pieces, and I think that is unique to lift itself. And I will speak about the main stepping stones to get to where we are now. So it starts in 1934 with Prandtl and Tejenes. They thought that air was initially at rest, then it would have an impulsive start and create a zero circulation around the airfoil, creating a separation at the trailing edge, which is creating the lift, which is just wrong. Air is flowing, as we know. We treat air as a flowing motion, as the airfoil as a stagnant object in space. So that is where their theory lacks. But where it allows us to advance is it brings up the circulative air around the airfoil. That is extremely essential for lift. It is one of the main things to create the lift as our understanding stands today. The next one I will talk about is the flow field fallacy. The flow field is essentially just particles moving, in this case, around an airfoil. It is just how the particles flow. And the flow field fallacy makes a false cause and effect. It makes the argument that lift is only caused by the flowing of the air. It is just flowing over and lift is being created. Now again, that is just not how it happens. There are other things that matter. It is the velocity of the air, it is the density of the air, in which I will talk about later. But where this lacks again is the detail. It doesn't explain enough. Then the next most common example where most of these theories are actually based from, I didn't name any just because it would have been redundant, but Bernoulli-based theories. They rely on Bernoulli's principle, and that is a higher velocity moving air creates a lower pressure zone, which again, just as the other two theories that I've mentioned, it does have some relevance to our theory today. It said that because of these lower and higher pressure zones at the top of the airfoil that is created because of the higher velocity and the higher velocity, lower pressure, and then the lower pressure, or the lower velocity, higher pressure, that this is what is lift. And like I said, it's similar to the flow field fallacy, which is the base of, actually the Bernoulli principle, is the base of the flow field fallacy. But it fails to mention everything else just as the other ones. But these three theories were the essential stepping stones that we had to take to create our theory of lift as it stands today. So, time to go over our actual theory of lift today. So, for simplification, I'm going to just say that the airfoil is stagnant in space, and then the particles are moving. Although planes do move and everything is moving, for the scope of this class, it is much easier for me to just say the airfoil is not moving and the particles are moving above. So, as the particles are interacting with this object in space, they are coming over, as this picture, it's a poorly drawn picture, so ignore that, but the particles are flowing over the airfoil, adhering to the wing due to this phenomenon called the Kondoa effect, which is the adherence properties of fluids. It is flowing over the airfoil and down the trailing edge, creating a pressure gradient at the end here. This pressure gradient is pushing the back of the wing down and forcing the top of it up, allowing it to create the lift. Now, that leads me into my next what else is a very imperative part to create the lift? It is the wing shape. Not all shapes can create lift. If I throw a block, if I put a block in a wing tunnel, it's not going to create lift because it is a symmetric shape. There will be no pressure gradient, which is why airfoils look like the teardrop shape to create that. How I want to describe this is two particles are moving along into this teardrop shape, and they are together, they are linked. So they leave the trailing edge at the exact same time. Now, because they leave at the same time, the one above, because of how the teardrop is shaped, it has to go a longer distance to reach the trailing edge. So it has a higher velocity, which explains why there is a lower pressure, because we do know the thing that the Bernoulli-based explanations rely on. It is true. It is true that the higher velocity would be over the overarching trailing edge, overarching region, and then the lower velocity creates a higher pressure, creating that pressure zone, creating this phenomenon called vorticity. The vorticity looks pretty much just like a tornado, and it sucks the air through and back out of the trailing edge, creating the lift, adding to the lift. The next thing is the air velocity. You need the particles to be moving. You need them to have a positive velocity in order to get this effect. Then air density. Air density is extremely important for lift because with a low density, the particles would have such a low mass that the airfoil wouldn't be the airfoil wouldn't have much mass or force to interact with, creating less lift. As we know from physics, F equals ma, you require acceleration, you require mass. Without the mass, you cannot have the force of lift. And that leads me into the equation that I will be using for this class. Like I said, just for the scope of this class. For accuracy, I'd be using the Navier-Stokes equations, which is a series of partially differential equations which we cannot solve just yet. There are a set of equations to describe how fluids act and how fluids act under certain forces. But back to what I was saying, leads me to this equation. L equals C sub L, which is a lift coefficient that is to be determined experimentally. It is not a constant. It is something that engineers solve for in the moment, depending on the shape of the airfoil, assuming it is similar to this to even create the lift, or if it is the velocity that they're planning on going, which again, just for simplification, I'll just say the velocity of the air. Then it is rho v squared over 2, where rho is air density. Again, it's extremely essential to have that air density. V is the velocity of the air, and A is the airfoil area. And as you can see, if the area is far too small, then it is going to restrict how much lift you're going to be creating. All of these are extremely essential for lift. And like I said, the problem with these, and finally, the problem with these theories is not that they're totally wrong, it's just they're missing a large piece of this puzzle. I think that lift is a huge puzzle that we're still solving today. And as we advance in math and physics, then we will fully understand lift and be able to use it to our advantage rather than almost fighting with it. That was my honors project on lift. Thank you.